Okay, welcome everybody to this month's edition of the Chalmers AI for Science seminar. It's our distinguished pleasure to introduce Pratyush Tiwary, who is an associate professor at the University of Maryland, College Park, in the Department of Chemistry and Biochemistry in the Institute of Physical Sciences and Technology. He received his undergraduate degree at the IIT in Varanasi, India, and then moved on to Caltech to do a PhD in material science. And he has been doing postdoctoral work at the ETH in Zurich, Lugano, and at the Columbia University in New York. His work is at the interface of simulation, statistical mechanics, and machine learning. And he's already been awarded several prestigious awards, including the NSF Career Award, the NIH Maximum Investigators Research Award, and the ACS OpenEye Outstanding Junior Faculty Award. And with this, I'm happy to hand it over to you, Pratyush, and we are very much looking forward to what you have to say today. Please take it away.
Is it visible? Is the screen visible, Simon?
Yes, it is visible.
Okay,
thanks.
perfect. Perfect. Let's get started. So thank you very much, Simon, first of all, for the invitation and for the introduction. And I'm very, very excited to be speaking in this forum. I watched the last couple of talks offline, and they were really, really nice. So let's get straight to business. So I'm at the University of Maryland. I have been here for a little over 5 years, and my group is really thinks about AI, statistical mechanics, and molecular simulations in a very integrated manner. So the big picture of today's talk is we don't think about AI as, so we don't have this perspective that chemistry is an application area for AI, where AI tools as they exist can be applied to problems in chemistry. We also don't have the perspective that, which often chemists have, that AI is a way to analyze data in chemistry. So these are two views that are quite common currently. And our view is, no, it's a bit deeper than that. AI and chemistry, especially theoretical chemistry, can be deeply integrated in a variety of ways. And I will be telling you about a couple of papers today that my group has very recently published. The first one just got accepted in Nature Communications. So it's not, the archive is not the actual paper. And I will be telling you how we do all this. So as we proceed further, I want to thank the organizations that have supported this work. And my group, of course, we have a rapidly growing group with close to 10 or 11 PhD students and 3 postdocs. We do have opening for at least 2 more postdocs. And I can say with confidence that my group is the only group with a postdoc in the group. You can see him in the virtual background behind me. And if I remove the virtual background, he's actually sitting right there. And he will be helpful today to explain some peculiarities of diffusion models. He will be there to explain those to you. So, okay, so the last couple of years have been really a poster year for AI and molecular simulations. On one hand, we have work coming out of Romy Amaro's group, which is simply beautiful. I mean, we are doing billion atom molecular dynamics, simulating every water molecule in fine resolution and really seeing what's going on. So this picture was featured in New York Times, and really in the middle on 2 pages. At the same time, we had AlphaFold, which really took everyone by surprise, and not just theory people, but also experimentalists. I mean, everyone is using it. It's really been explosive. And I think perhaps that AlphaFold is the first time that AI-related technology has been awarded a major prize. It's not the Nobel Prize, but it is quite something that Demis Hassabis and John Jumper were awarded the Breakthrough Prize in Life Sciences. It just shows how much excitement and how much potential is there. So this raises the question, are we there yet? Are all exciting problems solved? Are we short of problems to solve anymore? So the answer is no. First of all, AlphaFold itself has many, many issues. It's a way of going from a sequence to structure. It does not really have notion of ensemble of structures. People realize that by making AlphaFold weaker, you can start to get ensemble of structures, but that's not a Boltzmann ensemble. By making it weaker, you can also start creating junk structures to get a sense of the energy landscape of a protein. For example, this is T4 lysozyme, where a single point mutation changes the energy landscape quite drastically. Effectively, it boils down to where a side chain is oriented. And if you run these 3 sequences through CollabFold, you will see that it does not quite get it right. Overall, the RMSD is correct because this is just a teeny mini side chain. But now if you think about drug design perspective, if you think about how a ligand can go in and sit inside this pocket, whether this side chain is blocking the entry or not is the most important thing. So these are problems which are not exactly solvable by AlphaFold. Another problem, which I think is even harder, and I'm just making, building up on the name of AlphaFold. So let's think about an alpha RNA, which solves the RNA folding problem in the same spirit as AlphaFold for protein. And I would like to argue this is perhaps 50 years away, for the simple reason that the number of PDB structures for proteins is so much more than the number of PDB structures for RNA. In fact, if you plot how the number of PDB structures for protein has changed as a function of year, the predominance of AlphaFold in the last 2 years also coincided with a very huge number of structures just starting to come up. So RNA, we are really training data limited, and RNAs matter. RNA matters because, the known number of human RNA is more than 10 times the number of proteins. And even though that is true, the number of RNA structures is, as you can see here, less than 1% of proteins. And there is a huge design space available here because the number of FDA-approved drugs that target human RNA is 2. So there has been progress in this. Riju Das's group at Stanford came up with a paper shortly after AlphaFold, which was also on the cover of Science, where using some sort of geometric deep learning, quote unquote, they were able to get to 4 angstrom resolution. So there's a lot to do here. And a yet third problem I would like to introduce is the problem of predicting phase transitions. This could be in hardcore materials, which is where I got my PhD. So, problems like when do defects nucleate in a nanopillar as you keep compressing it, or how do thin films grow? You deposit some atoms on the surface of a thin film. How do crystals nucleate? And how do proteins nucleate? And the nucleation of proteins is such a beautiful problem because it really integrates biology with material science, with chemistry, with physics, and it plays a huge role in diseases and things like Alzheimer's and everything. It's all about nucleation, but preferentially happening in one direction. So if you really want to look at these problems and predict what is the phase that is going to form, what are the competing phases that could have been formed, when are they going to form, what is the role played by the environment, these are problems which just a training data-based approach is not going to solve. We have to think a bit carefully. So my group has been working on all of these problems in different ways, including the problem of getting Boltzmann diversity from AlphaFold, RNA folding, and also phase transitions. Today, I won't be telling you about all the problems, or we'll be stuck here for a very long time, and I have to teach a class in less than 2 hours. So I will tell you 2 problems, 2 very specific questions I'm going to raise today and show you how we are trying to answer those. And then I will show you a little bit as to how do these questions connect to the bigger problems, the bigger challenges that I posed earlier. First problem is very simple, which is if you have a time series where you have observed some data just fluctuating as a function of time, and you want to predict what is going to happen next. This could be the price of stocks in the stock market. This could be the temperature of all cities today, and you want to predict the temperature tomorrow. And it's non-Markovian, by which what I mean is you cannot just, if you are at a certain point, you can see sharp fluctuations. It does not really mean where are you going to be next. You really have to take into account the history of how you got there. So this is a very, very, very general problem. And I want to make it a bit easier by saying that easier or harder, whichever way you want to think about it. Let's say you have some intuition about what's going to happen next. Or let's say you have some theoretical model which tells you that, okay, for the next 500 time intervals, this can actually not go much higher than a certain value. So how do you incorporate this knowledge into such non-Markovian dynamics that you have observed from experiments or simulations? This is the first question. The second question is also quite generic. Let's say you have performed a simulation or an experiment at 2 different temperatures, let's say a cold temperature and a hot temperature. And you have collected lots of information at these 2 temperatures, and you want to mix it together in order to generate information at some intermediate temperature. How do we do this? So in order to solve these problems, my group basically develops methods by integrating statistical mechanics with machine learning, with molecular simulations. And we have a range of methods. I invite you to go and check out our GitHub. Most of the methods also have nice little tutorials that you can just run in Colab and see how everything works. This has been one of the this information bottleneck work, which we first published actually in JCP in 2018, and then have been applying it to different problems. This is a big workhorse of my group. I won't be talking about it today. Today, I will be talking about these 2 methods. So let's start with the first one. So the inspiration really comes from autofill. This is a GIF that I found from, I think, Google's blog about LSTM. This is pre-transformer blog, where they show how do you predict text. So you write something and it says, let's get together soon for tacos. I think that's phenomenal, right? How did it predict tacos is going to come next? Last time it saw tacos was like so many words ago. If you think about it, let's say this is a character level prediction. So the number of characters you have to keep in memory is huge, right? It's a really, really long memory. And in fact, often when I'm having today Simon introduced me and I said something which was inspired by a conversation I had with Simon 4 years ago. So how am I accessing such arbitrarily long memories? So our inspiration was that perhaps this is also dealing with this non-Markovianity, these machine learning models. I will show you today results for LSTMs. I always get asked the question, how does it transfer over to transformers? I don't know the answer yet. So if you ask me later, we can talk about it more, but we're thinking about it. For now, I'll show you how it works for LSTMs. So the idea was quite simple. Just like you're doing, LSTMs can do autofill on text. If you could take a molecular dynamics trajectory where, let's say, you have a protein and you have monitored the end-to-end distance of a protein as you're pulling it, or you have some dihedral angle, and the dihedral angle, some feature of a protein, it is changing from one basin to another basin. So you can map it into an abstract language and do autofill on it. So it works quite well. This was the first paper we published in Nature Communications. And in 2020, I think Simon knows this paper. So in this paper, we did many things. For example, we took a riboswitch pulling trajectory out of Michael Woodside's group. So if you look at this trajectory from the experiment, you are monitoring the extension. How far are the two beads from each other? And you get a trajectory that looks like this. It's, again, highly non-Markovian. For example, look at this point over here. Something extension 710. So extension 708. It could be in this basin, it could be in this basin. You really don't know what extension 708 means unless you have studied where it was for the last many steps. So we can train an LSTM on this. So what we do is as simple as taking this from 0 to wherever it is, binning it into characters, so A, B, C, D, E, F, G, H. In my home language, in my mother tongue Hindi, you have more letters, so ka, kha, ga, gha, whatever you want to think about it. You have lots and lots of letters, and you do autofill on it. And now you can train an LSTM model which will spit out trajectories that are stochastic replicas of the input trajectory. So that's very important. It's not just committing it to memory. It's by basically it learns. I'm going to be a bit quick here, but effectively the embedding layer that you have here captures the true kinetic distance in the actual system. So now you can generate probability distributions and see you can correctly write exactly correct probability distribution, exactly correct kinetics. The competing model here is hidden Markov model, where while this is non-Markovian, you can connect a fictitious Markovian model in the back, a Markovian parameter in the back, and then you can do prediction on this. But there is a hidden variable that is still Markovian, right? So at some point, hidden Markov model breaks down. So here I'm showing you the number of transitions between different points, like number of transitions between 710 and 700. And it does a good job of capturing the trajectory, but it's not perfect. LSTM, on the other hand, you cannot tell whether it's a LSTM trajectory or it is a input trajectory. So this is cute. This is not exactly useful. I would call this being cute. Why do I call it cute? So what you could do, for example, if you ran an experiment and a reviewer said, well, you have only one time series, can you generate more copies of the experiment? You can just train an LSTM and generate copies of the trajectory, and no reviewer would be able to tell whether it is a fake trajectory or a correct trajectory. So in a sense, you are doing deep fake on molecular dynamics trajectories. So people thought that could be useful. The reason people thought that could be useful, for example, is because molecular dynamics simulations, where you are just simulating how atoms talk to each other by solving Newton's law of motion, have a timescale problem. So this DESRES here is an acronym that many of you might know, many of you might not know. It's a very, very special supercomputer known as Anton, made by the D. Shaw Research Company, which if you put in the total number of dollars he put into the computer as well as human resources, it's probably a few $1 billion at least, which runs faster than any other computer in the world. So the idea was that if for a biomolecular system or a molecular system, you have a relatively short trajectory coming out of Anton, you could train such simulators, LSTM or some GAN or whatever on it, and to generate longer trajectories. The problem here is that even the best trajectory coming out of the fastest supercomputer in the world will still have some statistical error, simply due to thermal noise. So this is not a D-Shaw trajectory. This is just an MD trajectory from my local computer. not even a supercomputer, but for the sake of illustration. So here you can see that in this trajectory, there is a peptide which can exist at a left-handed helix or as a right-handed helix. Nature does not prefer left-handed over right-handed for this system. It's actually symmetric. And the force fields also, if you ran it long enough, you will get symmetric population. You should not see a preference of one symmetry. It's a chiral system. But if you run MD, molecular dynamics, just solving Newton's law of motion, and by the way, I'm not showing you the water molecules that surround this protein over here, you would see that one of the chiralities dominates over the other chirality. And there is nothing special about the right-hand side dominated over the left-hand side. Maybe the next 20 seconds, the left-hand side dominates. So this is the free energy, which lower free energy means higher probability. That's the idea over here. So now if you train your LSTM on it, LSTM is like a very good undergraduate student who just copies everything to memory, does not really think about what is the big picture. We don't want students like that. We want students who can see what is the big picture. So LSTM does not quite pick up the big picture. It just commits everything to memory. So this is an ensemble of LSTM generated trajectory. That's why you see error bars. And it's exactly the asymmetry that you saw in the input trajectory. While if you ran the MD 10 times longer, you would see that this noise averages out and you get a nice symmetric population. So how do we account for this? How do we, you can call it an inductive bias or whatever you want to call it. How do we tell the machine learning that there is a certain symmetry, which we know from intuition or from other theoretical calculations? These could be free energy calculations that you need to input. So normally when we want to add constraints to a machine learning model, we just take a Lagrange multiplier and add the constraint. That's how autoencoders work, for example, or a variety of architectures. In recurrent neural networks, this is difficult. Why is it difficult? Because anytime you add a constraint, you have to go back and unwrap the full trajectory for arbitrarily long times and run everything to calculate the effect of the constraint. So it's not easy to backpropagate the value of the constraint through simple training. You have to think a bit carefully. So for this is where what I mentioned earlier, deep integration with StatMech came to rescue. So one of the key ideas that helped us was this. We had realized in the first paper itself 2 years ago that the loss function of an LSTM is actually very similar to the path entropy from statistical mechanics. So what do I mean by path entropy? By path entropy, I mean something that looks like this. So this is a bit technical, but I will try to give you a flavor for it. Especially many of you might be familiar with maximum entropy methods coming out of E.T. Jaynes, who was 30, 40 years ago, a really, really fantastic person, scientist. So what E.T. Jaynes said, that anytime you're trying to build a model of a system, you maximize the entropy. In a crude way, you minimize your assumptions about what you don't know. So for example, if you want to come up with a model of, let's just leave it at that. So it's a maximum entropy model means that you are fitting to what you know while being least unbiased about what you do not know. So that's maximum entropy. Here I'm talking about maximum path entropy. So similar idea, but you're not talking about states. You're not talking about probability in grid points. You're talking about probability of paths that you might take in going from one place to another. So what we showed in this paper is just like predicting a single text, a single word here in the embedding layer can be considered as a state of a system, a state in the embedded layer. But a sentence itself is a path through this embedded layer. That's the key idea. So when you're training an LSTM model, you're essentially maximizing this path entropy. And now in statistical mechanics, the way models are derived is you maximize the entropy and you add constraints to this. So if you have done any statistical mechanics, you would remember these constraints correspond to constant, the number of atoms in the system or the temperature of the system, and you can derive different ensembles from it. You can derive what is known as a canonical ensemble, as a grand canonical ensemble, all those types of things. So here we have a similar path entropy, and now we can add constraints, and these could be dynamical constraints. These could be constraints about the diffusion coefficient of the system or whatever you have. And together they are known as the caliber. Okay, so this is the path entropy, and this is constraint on some dynamical observable. So what we can do now here is, now let's get back to LSTM. So we showed that LSTM training and LSTM is similar to maximizing this path entropy. So now we can add constraints. Let's say our constraint corresponds to the population of the relative population of these two states. So probability of being left-handed helix, probability of being right-handed helix, their ratio, that is S. So what we can do now is to connect paths that follow a certain probability of the two helices with some other paths that follow some other probability of the two helices. So for example, here we could say that both helices are actually symmetric. And here we could say both helices have a 10% asymmetry. And now we can derive a relation between these two path probabilities. And we have a Lagrange multiplier here. And this actually goes back to ideas proposed by David Chandler and Juan Garajan back in the day. They call it tilting of path ensembles. So where you have, this is hardcore StatMech, where you have really observed probabilities with a certain path. And by adding values of something that you want to change about this path, you can generate paths with a certain other probability. The problem they had was they did not know how to calculate this value of lambda. So what we show in this paper, which we call path sampling LSTM, is that we can actually very quickly calculate the value of this lambda. And then the idea I will describe to you briefly. So it's a bit technical, but I think it's worth it. So let's say you have a trajectory that you have observed. It's poor training data. It has some issue, which is all true for almost everything in life, right? We don't have perfect training data. But through intuition, you know that this is the error. This is what needs to be corrected. So what you can do now is to train an LSTM model on this, which will, on an average, follow this path probability as you see over here, right? This ratio of helices. It will have that error. But the point is that you can correct it. It's while the mean is somewhere over here and the 5% and the 98% confidence intervals are somewhere over here. If LSTM does a job of generating stochastic trajectories, so if you take this LSTM model, you can generate actually lots and lots of trajectories. On an average, it will follow the mistake that you had in the initial training data. But once in a while, you will get trajectories that are tilted in the right direction. So you subset those trajectories. You have to, however, keep in mind that you have biased your input path ensemble. You have selected a subset of trajectories. So you need to correct for this weight. And that weight comes through this lambda, through this Lagrange multiplier. And here, I won't go into how exactly we calculate it. You can read it in the paper. It's quite simple. It's just a linear problem that we can solve to get the value of lambda. And now we have a subset of trajectories with corresponding weights. And we can train our LSTM on this subset of trajectories. And now once you take the trained LSTM with this path sampled, you get exactly correct population. And that's how it works. So this is for a simple protein. And you can see how it resolves the issue. I will skip this one, and I will show you how it works for things which are quite different from proteins. This is, if you have done any quantum mechanics, one of the things I really liked when I did quantum mechanics in grad school was these ladder operators. They're so beautiful. This comes from the idea of second quantization and all that. So here you have a cavity. And in this cavity, you have a two-state atom, which can jump between this state and this state. And it is decaying photons every time something is going on, and photons are being observed decaying through this cavity. So this is a symmetric system. And now due to this, it becomes a dissipative system. So the thing to keep in mind here is what you can control is the dissipation rate of the photons. And you can observe trajectories for a given dissipation rate. So here I am plotting you the number of photons that were emitted. And remember, quantum mechanics, particles are waves, waves are particles. That's why the number of photons has these wave oscillations. So quantum mechanics is, of course, funky. So if you get different input trajectories, you will see how it behaves like this. There is wave, it drops down. And if you average over all of these trajectories, you get a very interesting behavior where it's a decay, but with oscillations that are dominant early on. These are known as the Rabi oscillations, if I remember correct. So this is for a certain dissipation rate. And this is not an experiment. This is a Monte Carlo simulation using this software known as QTIP. So if you fit your LSTM to it, once again, it does a wonderful job of capturing this trajectory. And now the question is, could I generate a trajectory for another dissipation rate? So now my observable is the dissipation rate. So again, by tilting my paths, by doing the path sampling, I can now generate trajectories that correspond to a dissipation rate, which is twice of what you saw over here. So you see it goes down to zero much earlier than this one. And again, if I ran a new experiment for this dissipation rate, the LSTM fit it correctly. And you can see this is a highly non-trivial behavior. This is not just simple sinusoidal multiplied by an exponential. It's really, really complicated and highly non-Markovian, and it is able to predict that. So that was the first part of the talk. And I guess we will have questions at the end, and I will be happy to answer any questions then. I want to quickly show you about the second part of the talk in maybe 15 minutes, and then we will stop for questions. So far I showed you how can we do time series prediction on highly non-Markovian time series coming from simulations or experiments on proteins, on RNA, on quantum systems, where we are introducing our intuition into the training. The second part of the problem is the problem that I posed earlier, which is how to predict physics at one temperature from experiments conducted at other temperatures. So in chemistry, there is something known as Arrhenius law, where if you have observed rate at one temperature and you have observed rate at another temperature, and certain systems are very easy, they follow this Arrhenius kinetics. You can just fit a simple line on a log-log plot and get the rate at any other temperature. So this could be the time it takes to fold or whatever like that. But often many systems are what is known as non-Arrhenius. They don't follow such a simple linear behavior. They can be anything. They can be convex, they can be concave, they can be a mixture of these things. So in order to mix information across two temperatures, there have already been approaches. The most popular one is something known as replica exchange molecular dynamics. This was published in 1999, but the paper actually the idea back to much before that, from Giorgio Parisi, who won the Nobel Prize last year for physics, and that idea is known as simulated tempering. There is the same idea effectively, with some changes, that you simulate the system at two temperatures. So at your low temperature, your molecular dynamics is trapped in some state, because if you have a very high barrier, you're not going to cross it to go to the other side. At high temperature, it's like you're just jumping around from every place to place. You have so much energy, you have no problem going over the barrier. So what replica exchange does is to periodically exchange the coordinates between the low temperature simulation and the high temperature simulations. So it's as if through magic, it appears that the low temperature simulation is suddenly in this other basin. It never actually crossed the barrier, but just because you exchange information, once in a while you exchange information when the high temperature system was in this basin. So that's how it looks like. So this is one way to really use information from higher temperature to go and sample better at lower temperature. This replica exchange molecular dynamics has a curse, which really comes from statistical mechanics, which is that when you try to exchange information between different systems, actually it comes from central limit theorem, not even statistical mechanics, due to the Gaussian distribution. And you have a distribution of energies, and this distribution of energies must have an overlap for this exchange to happen. And this distribution of energies becomes tighter and tighter as 1 over square root of n as the number of atoms increases. So if you have, let's say, 100 atoms, it's very easy to get exchange between different things. If you have 100,000 atoms, the exchange probability actually goes to 0 as 1 over square root of n. So it really starts to fall down. So people have tried to come up with many tricks to solve this problem. One of the big workhorses in this area is a method known as replica exchange with solute tempering, where you don't exchange all coordinates. Let's say you exchange only a little part of the system. But it has its own approximation. So what we would like to do here is to use generative AI to solve this problem. So the inspiration is quite simple. If I was giving this talk in a seminar room, I would have asked you to raise your hand and tell me if you knew the name of this character. It's one of my favorite comic characters. In India or in the US, he's known as Getafix. In France, he is known as Panoramix, and I think in Germany he has some yet another name, you know. So he's from this Asterix comics. He's the magician he's the druid of the village, and he has this magic pot. And from this magic pot, he can pull out anything. And one of the things he pulls out is basically this potion, this magic potion that he brews here that makes the villagers very, very powerful. So what does Asterix have? What does Getafix have to do with molecular dynamics? So the idea is simple. Let's consider each of these replicas as having sampled the system conditional at that temperature. So this very hot one sampled it conditional at T extra hot. This one sampled it conditional at T hot. This one T cool. This one T cold. And you did not get exchange between them, just molecular. Okay. So you say, well, there was no exchange. What do I do? But now Getafix comes in and takes all of these conditional probabilities and mixes it in this magic pot. And then he post-processes them with denoising diffusion probabilistic models, and I will tell you about that, to generate the probability distribution at any temperature, not just these 4 temperatures that you studied, but a temperature in the middle, or a temperature on the left of the ladder, which you never even simulated, or the temperature higher of the ladder. And perhaps even at this temperature, since you did not get exchange at the coldest temperature, it does a better job of generating samples. So some of you are probably familiar with denoising models. Let me remind you of what they are. And this is where the postdoc of the group comes into picture. So I'm very proud of this paper because while many of us have published in PNAS, which is a prestigious journal, how many people here can claim to have published a photo of that dog in this journal, right? So this was figure 1 of this paper. So I'm really proud of this. I don't know what that says about me. So this is a photo of a dog. And let's say you want to generate photos of other dogs. You cannot do that just on the basis of one dog. Maybe some fancy one-shot machine learning can do it. But the idea being that if you have seen faces of maybe 10,000 or 1,000,000 dogs, a picture of a dog is a data point in a very high dimensional space, right? It's 1,000 by 1,000 pixels, and with color channels for everything. And you have some complicated probability distribution that exists here that tells you how does this data point connect with this data point, so on and so forth. So you have these pictures of dogs. In this case, I'm showing you the picture of my dog Pakora. And you could sample from this probability distribution. The problem, of course, it's complex. There are correlations across all length scales. It's hard to do that. So there are many ways of generating more faces of dogs. What diffusion models do is to add noise to this. So they keep corrupting this, and there is a forward diffusion process where instead of a very high dimensional data set, you keep the dimensionality of the data set the same. So there is no dimensional reduction here. DALI does dimensionality reduction, but there in this model, what I'm showing you, there is no dimensionality reduction. So you generate a data set at the same dimensionality where everything is no noise and everything is independent of everything. So this is great because generating more noisy data points is trivial, right? It's just white noise. It's so easy to generate more noise. Problem, of course, is you have lost all information. So now you can train a bunch of neural networks which learn the backward diffusion process. And given this noise, they learn how to denoise. And through this backward diffusion kernel, they generate photos of, again, dogs. In this case, this is completely stochastic. So if you compare it with, say, Frank noise normalizing flow, the same data point here in noise will not go back to the same dog. It will always go back to something else. But if your training data set is big enough, what you're guaranteed, it will go back to a photo of some dog. So that is the basic idea. So let's go one step further. Let's go from dogs to humans. So this is a photo of 5 people. This was actually my student Yehang's PhD committee. So what he did was to say, let's say I have trained, what he did actually was to take a machine learning model and train it on faces of lots and lots of humans. And then he said, let's mask the right side of the faces of his PhD committee members. And then ask how does the DDPM do in predicting the right side of the face, conditional on seeing only the left side of the face, number 1, and conditional on having been trained on many faces where both sides have been seen. This is quite important. So it does a decent job. It makes me look way older, which I'm annoyed by. But for John Weeks, who is already kind of old, he was like, oh, I look very handsome. It does a very good job. Some random hand comes on his shoulder over here, but otherwise, there are also systematic biases here. It does a better job in predicting faces of Caucasian white males. That's all biases in the training data set. So how do we go from faces to molecules? So what I showed you here is, in a way, what is known as in-painting faces. You're missing some part of a face and you're generating that remaining part of the face. So just like that, it's important that you have seen faces that have both sides of the face for some people. If you have never seen a human who has both left side of the face and right side of the face, it's not going to work. That's important. So how does it come to molecules? This is an RNA molecule over here. And here at very high temperature, you should have seen everything. That is the pink region. At low temperature, you are trapped. Wherever you started, you get trapped over here. And now we mix this all together in the magic vessel that I showed you from GetAfix. And just like I could do in-painting in faces, I will do in-painting in conformations. So this is how it looks. So this is a 4 nucleotide simple RNA molecule, which is a baby RNA molecule, GACC. And when you do replica exchange molecular dynamics, at the lowest temperature, you never sample this state. So this is like the right hand side of the face. This is missing. You did visit this at the higher temperature. But since you had, this is in all atom water, the exchange probability was so low, it was like 0.1%. You never actually got to this basin at the lowest temperature. But now when you do DDPM on it, you do get that sample again. That is generated correctly. If you ran much longer unbiased molecular dynamics, you would see that it is indeed sampled and you get the right population. And with this, we can also do RNA folding. I will skip this slide. This is unpublished work, but this is just much more complicated systems where you start with Rosetta and try to really predict the folded structures of RNA, the full ensemble. So keep your eye out for this paper. And this is how it looks, so let's pause this movie for a bit. So this is a peptide with 9 residues. So the training data set here is the dihedrals of these 9 residues. So I'm not putting in the coordinates of every atom. I'm putting in the dihedral angles for these 9 residues. So that 2 multiplied by 9, 18, but not just the dihedral, I'm putting the sine and cosine of the dihedral. So something like a 36-dimensional space is where the DDPM is working. And I'm showing you 2 coordinates from that 36-dimensional space. So you start from noise, and each of these is one data point that you have sampled from noise. And you generate, I'm showing you the effect of the backward diffusion here. When you start from noise and you keep running the process, you will generate some other data point. But let's say you have 50,000 input points and you run the backward diffusion process and you collect where do they go. This is how it looks like. You see how structure starts to emerge, and it gets the basins and it gets the probability distribution. There are some outlier points here. This is sort of hallucinations. These points don't make many sense, but their Boltzmann weights, their free energy are so low that we know how to exclude them. And another reason why I'm really fascinated by denoising models is because the first denoising model paper was 2015, which was really called Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics. This is Yashov Dixtein's paper and Surya Ganguly. And this paper really said, oh, thermodynamics is really cool. There is a thing known as diffusion and Jarzynski relation, and we want to get inspired by all that and do better machine learning. And then the paper kind of disappeared until the last 2 years when it has really exploded. And in fact, this year in ICML, and other workshop, diffusion models just took over everything else. And with DALI, we have all probably used diffusion models, one form or the other. And I think this is possibly close to my last slide. And this is kind of technical, but very interesting. So what I showed to you is that how diffusion models can surmount problems with very poor exchange, right? But you still have replicas and you're every once in a while exchanging information. So we pushed it to the limit of no exchange. So the name here is a pun on folding at the home, started by Vijay Pandey. So I'm calling it replica no exchange at the home. So the idea being that now I could run replica exchange on different computers, one in Brazil, one in India, one in China, one in Sweden, that are not talking to each other, and then mix all the information together. So this is the same 9 residue peptide that I showed you earlier. And I'm doing replica exchange at 400, 412, up to 500 Kelvin, so maybe 12 replicas, and 0% exchange. They're completely independent. So when in orange over here is the benchmark from a long unbiased simulation. You see that DDPM, in the basins, it does a good job of getting the probability right. In the very high states, it fails down. There's a competing method known as multiple Bennett acceptance ratio. This was a bit disappointing because MBAR, which is much easier to run than DDPM, was getting the same accuracy at the lowest temperature. But now we push it even more. We ran our simulations till 400 and we asked, how would the simulation look at a temperature much lower than this lowest temperature, 350 Kelvin? Here, MBAR totally fails. And here you can't do unbiased MD because this system is so slow. So here we do well-tempered metadynamics with a very optimized reaction coordinate, which we have reasons to believe is converged. And there we see that DDPM agrees with well-tempered metadynamics actually quite well. To push the temperature even further, it's still in the basins, this part of the landscape, it still does a very good job of agreeing with it. But it is in this part of somewhere it plus starts to fail. So this, we were so shocked by this result that we did not put it in the main paper. We put it in the supplement of the paper and think we have better understanding of why this is happening, but we still don't have a mathematical proof. And the reason why this is really happening is that at highest temperature, at 500 Kelvin, you are sampling everything. So technically speaking, you are following detailed balance at 500 Kelvin, and that information is being percolated through. So I can summarize my presentation to you now. So I showed you basically denoising diffusion models and long short-term memory networks. In denoising diffusion models, I showed you how we can make use of information from different temperatures at same temperature, at some temperature of interest to generate more data. There's nothing special about temperature. We can do this with other parameters, other physical observables that you want to control, and we are working on that. And then I also showed you some results with long short-term memory network where we had non-Markovian dynamics and we added intuition or some existing theory into it to do prediction. I did not talk to you about information bottleneck method, which we are applying for different types of problems, including the problem of adding Boltzmann diversity to results from AlphaFold 2. And if you go to our GitHub, you will find all sorts of codes. And with that, I will be happy for any questions.
Thank you, Pratyush, for a very nice and interesting talk. Very impressive amount of work that you managed to fit into this 40-minute presentation. So there's a bunch of people clapping for you in the reaction. So there's one first question from Louis Tunstall from Hocking Face. He's asking, does the conditional generation with in-painting use images as inputs or some other modality?
Yeah, so for the phases that I showed you, it uses images, but for the actual application, it uses molecular descriptors of the protein. So here it uses phases. But what we are really doing is this one. Here there is no phases. So here I don't give it the coordinates. Here I give it what are known as order parameters. So for example, here it works on a 100-dimensional space, which corresponds to the dihedral angles of these things or the distance between these different parts of the RNA. So there is a bit of feature engineering that is going on here. I hope that answers the question.
Thank you. I think so. There's a question from Chris. He will ask this question himself.
Okay.
Hi. I don't think I can start my video because I'm not a co-host, but yeah, anyways. Hi, Pratyush. Very nice talk. I really like the combination of so many techniques from so many different disciplines. I have a question regarding the first part of the talk. So in the ps-LSTMs, you said that you need expert knowledge to correct a certain bias that you observe in the data. Now, have you thought about ways of incorporating experimental constraints to substitute the need for intuition or?
Oh, absolutely. Absolutely. The expert knowledge could be coming from experiments too. Absolutely. Right. Any knowledge that you want to add. But here is a big open theoretical question that I don't know how to answer. But I showed you here, I added one constraint at a time. Okay. You might have 2 constraints. You might have 3 constraints. You might have 4 constraints. Right. I think I know how to do it for 2 constraints at a time. For 3 constraints at a time, I don't think the method will work unless we are willing to allow error bars in the constraints themselves. So that's a very interesting open direction. But otherwise, the constraints could be theoretical, they could be intuition, they could be experimental, no problem.
Right, right. So have you tried it with experimental constraints also?
No, but I'm 100% confident it will work. Okay. So we can look at it together if you want.
Great, great. Okay,
yeah,
thank you.
It's effective. It's really the same thing. So right. I mean, actually, if you think about this quantum thing, this is an experimental constraint, right? The experiment, quote unquote, here being the Monte Carlo simulation carried out through QTech.
Right.
Right. So in a sense, this is an experimental constraint.
Right.
That's what I'm saying.
Great. Thank you.
No problem.
Okay, and then we have a question from Saswat Party.
Yeah, I'll read it. So also related to low high temperature example, is the magical exchange of coordinates supposed to emulate a scheme where you heat and cool the sample repeatedly? Maybe, maybe not. I mean, what you are saying, heat and cool the sample repeatedly, goes back to Parisi's simulated tempering. So I would say no. That's simulated tempering. That's what is done is simulated tempering. This is different. This is, you have already done the heating and cooling, and you have different copies of the sample where you try to take it to different temperatures, and now you're done. What can you do better? And this connects to the question from David Rosenberger, so I will answer both of them together. Regarding no replica exchange, if the highest temperature is the most informative, why do you need more than one replica? Haha, very good question, David. So I'm very happy that you asked this. So let's go to a protein. This really boils back to the energy landscape of a system. And here I can show you my RNA slide. So this is an RNA molecule. For many systems, the free energy landscape kind of stays the same across temperatures. Certain features changes. The ratio, the relative probabilities of features change, but the qualitative nature of the features and their ranking stays the same. But that's kind of when you get lucky. replicated systems, even if you change the temperature by 10 degrees, everything changes. Think about life, right? We exist at 37 degrees Celsius, our human body temperature. If we went up to 42 degrees Celsius, everything changes, right? 5 degrees Celsius is already too much of a temperature change. So the reason why the highest temperature replica is not informative, it's useful. It's useful because it goes to these other basins. Useful is not the same as informative. Even though it goes to other basins, the probability distributions are totally skewed. That's why we have to reweight it to get the probability distribution at the right temperature. So the example that I showed you here, this was actually a bit of a simple example, because if you look at it across the temperatures, this state is slightly more stable. The one at phi 9 equal to -1 is slightly more stable than the state at phi 9 equal to 1. For most practical systems, this is because it's a tiny little protein. For practical systems, this is not true. This thing completely changes. So I hope that answers the question.
Thanks, Pratyush. I have a question myself. So as far as I understand, this replica exchange-based method, also this diffusion model approach to analyzing replica exchange and multi-temperature data, you are estimating a joint distribution of the kinetic energies and the coordinates. Is that right?
Correct. Absolutely correct.
So did you check whether the marginal distributions of the kinetic energies in your generated space follows a Maxwell-Boltzmann distribution?
I think we checked that. Yes. Yes.
Yeah. Because I mean,
that would be
in the
paper. We checked that.
Yeah.
No, it does. It does.
Yeah.
It does.
Okay. Because I
but
mean,
keep in mind that is an important point here.
Yeah.
We are not generating P of X comma T cold, but we are generating P of X conditional on T cold.
Right.
And
so this is
yeah,
so in the application scope. So you're estimating a joint distribution, but you're marginalizing over the temperature during inference. Okay.
Yeah, that's the important point.
Yeah. Okay. Thanks for the clarification.
No.
And for the sort of, I know your LSTM work quite well, but I'm curious to know if you've been thinking about incorporating other constraints. So you mentioned this constraint of, for instance, imposing changing the bias in the simulation due to finite sampling, but it could also be that you could use, say, for instance, that you know that the data comes from a stationary process, thereby enforce microscopic reversibility as a constraint. This is something that you
absolutely. Yeah, we would like to do that, and for example, think about this one. This is a trajectory where detail balance is not followed, right? It's a dissipative trajectory. Now you could ask, well, I don't know, maybe there is something forcing detail balance locally. How would it look like? We could try it. I'm a bit concerned because it's not magic. It will perturb it. If your constraint is so severe that it's non-perturbative, things might fail. So I will be cautiously optimistic. But I'm going to show you this one. This is a diffusion coefficient constraint. Here you are controlling the number of transitions. This is a kinetic constraint. So you can see here the effect of adding the constraint is actually raising and lowering the barrier.
Right. But I mean, you can still, I mean, if you have a system which is in equilibrium, right, you can still make sure that the sort of the effective operator that is generating the dynamical process that you observe, that is reversible, right?
Yeah. I think we could do a lot. And one open area, of course, is to start thinking about this with transformers, because LSTMs are hard to train. Transformers would be more fun. But I don't know, the first paper, I don't know how many of those parallels persist with transformers. So we need to sit and understand.
Yeah, I agree. But it's very exciting work. So I think we don't have any further questions immediate from the chat and from the audience, but we would like to thank you very much again for a very inspiring and exciting talk, and as useful, very energetic and good analogies to popular culture. So I think that's really wonderful. Thanks again, Pratyush.
Thank you.